set of questions in from people that I'll be talking about today. We'll see whether any other questions come in while we're live here. So the first question I have is an interesting one, the kind you face in office hours for any kind of class all the time. So let me first just read you the question, and then I'll tell you what I think about it. So the question says, I have a Shiny app that I made in R. So Shiny is a package you can use to create web applications that serve up the results of R applications. It says, we want to make it into a widget within Canvas, a learning management system, the Canvas LMS. The way third-party stuff plugs into Canvas is via LTI. That's the Learning Tools Interoperability Standard that was created by the IMS Global Learning Consortium. So the question is, how can we make any package in R, or especially a Shiny app, talk to LTI? Like I said, this is the kind of question I love to get in office hours because I can't answer it. I actually have no idea what the answer is. So what I would do if I had a student come to me and ask this kind of question is sit down with them at the computer and start to try to figure it out, right? I'm not going to do that here in these live office hours because I actually don't have access to the kind of computing infrastructure that I would normally use there in my office. But it's a great kind of question. And so what I'm going to do is bounce it right back to the class and say, is there someone out there who knows how you can make a package in R or a Shiny app accessible through Canvas using LTI? I'm also going to, of course, ask some people around here at Michigan. We have a group of people who've been involved in creating the LTI interface and so on, and I'm going to see if we can't get some of them to weigh in on this question too. It's great to hear that somebody's out there making a Shiny app so you can let people see the results of R through a web interface. And I look forward to seeing, what people are producing there. Okay. Second question that we have up today comes from a user who's interested in the applications developed here at University of Michigan that were highlighted in these week 5 video lectures, the lecture segments that we have. And this person asks about what it takes to create the infrastructure to develop these kinds of tools. What did we have to do here at Michigan in order to be able to do it? And notes that they're on the opposite kind of end of the higher education spectrum from Michigan, an open enrollment master's level institution. And so while they have some graduate students, they're not traditional in the sense of necessarily being available to work on projects on campus. So what are other schools doing to resource innovative development projects like this? So we talked a bit in the segments, the video segments this week, about a little about the history of how we got to these projects that we described this week, and also about the digital innovation greenhouse that we've now set up to really work on growing these projects to scale. So let me go back and talk about one of the projects in particular, because it's one of the ones that I've been involved with since the very beginning, the eCoach project. So eCoach is a computer-tailored communication system that we use to deliver personalized content to a large number of individuals based on information about them. I mean, in the most general sense, that's really what it is. You get a bunch of data about a lot of people, and you decide what you would like to say to each of them based on that data, and a system like eCoach lets you deliver that information. I came to this project, the eCoach project, from a problem that I faced, a problem that actually emerged out of my interactions with learning analytics. When we started doing the Better Than Expected project and trying to understand the performance of students in our introductory physics courses, it forced me to recognize the individuality of all the students who were in my class. To see, for example, that on the first day of class, they really weren't headed for the same place. Even though I gave them all the same class, they ended up in very different places in a way that was determined by where they started. And I really wanted to try and act on their individuality in ways that I hadn't before. I'd been teaching in a pretty industrial mode, kind of assuming every student was really the same. And I wanted to be able to now to tailor the way I interacted with students. So at just this moment, it turns out that one of my friends and neighbors here in Ann Arbor had won a prize as the University Innovator of the Year, which at a place like Michigan is a big deal. We have a huge university, lots of people here, lots of very innovative people. So if you're the Innovator of the Year, you did something pretty great. So this guy's name was Vic Strecker. He's a professor in our School of Public Health here at Michigan. And, you know, he really is an amazing innovator. I went to listen to Vic's talk. You know, he won a big prize. I'll go hear what he has to say. I didn't really know what he worked on at the time. And in doing that, I learned that Vic's work for the last 20 years has been in using computer-tailored communication to provide public health interventions, to provide really personalized coaching for people around public health interventions. Things like helping people control their diabetes or quit smoking or make some difficult cancer treatment decision. So he and his team of people at Michigan's Center for Health Communications Research had built this tool called the Michigan Tailoring System. And the Michigan Tailoring System is an open source software system that enables you to deliver content to individuals based on data that you know about them. It was exactly what I needed in order to be able to talk to my students in individual ways. So I did what academics usually do, and I went out for a beer with Vic in order to find out how this all worked and to see whether there was some way we could take his tools and turn them to educational purposes. And so we talked about, you know, what would be the strengths and weaknesses of this, what are the things you really should be thinking about, what are the lessons that were learned in the public health world about this kind of coaching that we might apply to education. And then we went out to try and find some resources to make this happen. At just this time, the organization EDUCAUSE had announced something they were calling the Next Generation Learning Challenge, with funding from a number of foundations, including the Gates Foundation. And they put out a call for proposals, and we wrote a proposal describing what we would do if we had some resources in order to make this project happen. It was a nice kind of proposal to write because there was a really strong framework behind it. The public health work that had been done with computer-tailored communication was very mature, well demonstrated to be effective, and also was sort of theoretically sophisticated. So we took that and attached to it the ideas about what we would do with education, and we sent this in. And we got a grant from the Next Generation Learning Challenge in their phase 1 first round grants. We got a grant here at Michigan, which we then used to hire a couple of people on a short-term project to try this in education. And so we were able to recruit an excellent young developer named Jared Tritz. We brought on one of my recently graduated physics students as the person to create the content for this system. So young people looking for a project to work on for a relatively short time, always an important resource on university campuses, and one that, you know, we use constantly here at Michigan for innovation purposes. So we brought a little group of people together, had a little bit of support from this outside grant, and we just launched a version of the project in our first year. That first version was very unimpressive in a lot of ways. It didn't look very beautiful. We didn't know that much about web design or anything else. But it was a good idea. The idea of being able to deliver computer-tailored communication was a good idea. And so it began to attract enthusiasm from other people on our campus. People who saw what we were doing and thought, "Ooh, I like that idea. I can see how we could make it better. I can see how we should perhaps think about adapting it for another class." We had people showing up wanting to be able to use a tool like this in their class. And so then we went the next round, and the next round was to seek kind of next levels of support. We wrote a number of applications for grant support. Of course, most of them we didn't get. It's a universal reality of applying for funds from places like the National Science Foundation or foundations, private foundations, and so on. You often don't get the grant. So we wrote, I don't know, 6 or 8 different grants over a period of a couple of years. And we did get a couple of them. So we got one grant from the National Science Foundation specifically to expand the use of eCoach in our very large statistics course on campus. That was a super successful project because we worked with some excellent people on the statistics side. Brenda Gunderson is a senior lecturer here, really fantastic instructor, very creative, very dedicated. She also brought a bunch of their students, both undergraduate and graduate students, into the project. Other statisticians, which made them eager to work with data, things like that. They did some really fun things with it. For example, when they wanted to convince students that what they were saying about what the students need to do to be successful was really true, they gave students the data and let the students analyze the data themselves. So that was one project. The NSF funded us to expand to statistics. We got a little money from the university to expand to chemistry and biology. So we got to the point where we had, you know, a project that was going and was actually serving about 5,000 students a term. But then that's when we really ran into the growing things to scale problem, because we'd been running the project all this time with a couple of young people who really weren't intending to continue to work on this forever. And it was happening in my lab, my physics lab, which is not really where this is even supposed to happen, or it's not a place that's set up for doing this kind of work. So at that point, we really faced a dilemma. What are we going to do to try and get this to scale? We were unable to simply take the stuff we had pasted together to make this project happen and carry it across to our IT organization and say, please run this. Because frankly, it wasn't that great. I mean, it really was not that well built because we had slapped it together in the way that we needed to create this system. So we really needed the kind of education technology accelerator, the kind of greenhouse environment that we've created with our Digital Innovation Greenhouse. And our need was so strong in a way that it drove me to go off and try and find a way to create such a Digital Innovation Greenhouse. I think that kind of structure that stands between individual class innovators on one side and organizational scale IT on the other side, that space probably needs to be filled on every campus, because there will always be things that you'd like to carry across that space. So I can imagine that many universities, IT organizations, the people sitting on the enterprise side, might be thinking about creating something like what we've created in our Digital Innovation Greenhouse. Perhaps taking some of the people they already have working for them and moving them in that direction, creating a small group of people whose job it is to be on the lookout for good ideas that are emerging on campus. Pick those ideas up and spend some of their time and effort on moving them to scale. It's a special kind of a job because it has to have a willingness to work with things that are ill-formed and that are sort of risky to work to use. So I think that it's a challenging job, but I also think it's a job that a lot of people in the IT world would find really interesting. I know here in our greenhouse, the developers that you saw speaking in this week's video segments, they're really excellent developers and they're really excited about what they're doing here in the greenhouse. It's really fun to do new things. So I think a lot of IT organizations could imagine sending some of their people down in this direction. So even though you may not be able to come up with a grant for a couple $1 million to just land a thing like this, just to create it ab initio, it might be that repurposing elements that are already present on your campus one way and another is a way to be able to grow these things to scale. Certainly the use of youthful talent is a crucial element. Here in the Digital Innovation Greenhouse that we have now, we have 3 full-time developers, but we have 10 student fellows of the Digital Innovation Greenhouse. Some of them are coding fellows, so they're computer scientists who write code. Some of them are user experience design fellows, people whose job is to think about the way we present the materials that we have to the users, to do a lot of field testing of the interfaces we're creating to make sure that they work in intuitive ways for our users. They're the people who are in some ways doing customer discovery for us, working with the community to understand what the community wants and needs, to think about how they can deliver the things that the community wants and needs. So user experience design people, and we're just now hiring some kind of innovation advocates whose job it will be to help us spread these things to communities where they haven't gone yet. So their job will be to look for and identify and then work with communities who may not know about the power of some of the tools we've created, but who we think might, if they knew about it, want to work with it. So these innovation advocates we're also hiring. So a lot of youthful talent, a few really hardcore professionals who are excited about working on this kind of thing. So I think being creative, of course, is always essential in innovation. Figuring out who has a kind of value proposition in working on an innovation. That can be on an academic side. It can be that doing an innovation can lead to the kind of publications that are really important for a scholar. So you might be able to attract some faculty members and graduate students and so on to work on projects if they see that there are scholarly outputs that might come from them. That might come in the form of research that demonstrates the efficacy of some new tool that you're building, right? This is one way of bringing people in. Another way of bringing people in is giving them work that's new and interesting and different from the work that they've done before. And so it could be that there are people working on the enterprise side of computing on your campus who actually would be quite excited to work on an innovation like this. And if their leadership allows them some space and time in their schedule to do that, you might find that they're quite willing to. So it's a great question. How do you make things happen in your own environment? And I have to say that for me, I've been here at the University of Michigan now for 20 years. And for the first 10 years that I was here, I kind of had no idea how to make everything happen on campus, because it's a huge campus with an enormous number of resources. So it's taken me a long time to learn kind of how to put all those pieces together. And one of the great rewards of being in this kind of mid-career part of my life is that I now have this network of connections all over campus, and I really like using it. So great question to think about. I'm also going to bounce this question out to the audience and say, there's a question here about how do other schools doing resource innovative projects, resource intensive projects like this, how do they get them done? What are some of the different models that people have followed? And I think that's a great question to share across the practical learning analytics community. And let's get some action going on the forums about this and see whether different places have offices like our greenhouse. I know there are at least several other universities that have created something that, at least in some ways, is similar to what we've done here in the greenhouse. So I think it's something that you might see emerge on more campuses. If you find yourself in a situation where you need someone to testify to the efficacy of this, feel free to direct your university leaders to me. I'm happy to talk to them about why we've done what we've done on this campus and how it's been a powerful tool. So I'd love to help make this kind of thing happen in more places. Okay, let's move on to another question. So we have another question here about what types of real-time in-class data systems I've found useful to be most impactful. And the question specifies that they're most interested really in text analysis tools, which we discussed a bit. But other tools that have been helpful for teachers while teaching would be interesting to learn about. So this is a great question too. As I've told you all, I teach a lot of big classes, and so getting interaction with students has always been a challenge. The very first kind of education technology thing that I did in my own classes was driven by this challenge of how do you find out what's really happening in the minds of 700 students when they're in a classroom. You can't say, does everyone understand? And expect to get any meaningful information from them. So this was in the mid-90s. And at that time, Harvard physics professor Eric Mazur was just beginning to launch what's become a very big project for him called the Peer Instruction Project. So the peer instruction idea is a mechanism for doing several things. One of them, though, is providing information to the instructor about what's happening with the students. In Eric's peer instruction model, what you do is you stop a number of times during class and ask a question. A question, well, in simple implementations, which is usually like a multiple choice question. So you ask a simple question like that, and then you give students a minute to think about it, and then you essentially require every student in the room to give you their answer, right? So this is where technology comes in. You probably need some technology to be able to gather all those answers. When I started, the technology was exceedingly simple. I prepared for every student in a class a set of colored cards that also had numbers 1 through 5 on them. And when I would ask a question, these were all tied together with a little piece of string so that they would keep them all together. When students came into the class, they would pick up one of these sets of cards. I would ask them this question. They would flip through their cards, choose the answer they have, and they would all hold them up. I could look around the room and see the colors to get a quick sense of about how many people were answering the different answers. It wasn't fully anonymous. Students could see one another's answers, but it was actually quite awkward for them to sort of turn around and crane their head around the room and see whether they could see all the answers. So it worked actually remarkably well. It didn't allow me to record data very well, but I wanted to. So in that first semester, I actually videotaped all the classes so that I could go back and look at how many people were answering right and wrong all these questions. So that was one example. And this is, of course, turned into the world of clickers, electronic response units that many instructors now use as a part of creating a more active environment in the classroom, but also providing immediate feedback to the instructor about whether students are all getting the question right, or maybe they're all choosing some distracting answer. Maybe they're spread all over, no one has any idea. That's one way of getting real in-class feedback, through asking questions and then getting responses from students, whether that's an electronic system like the iClicker system we use here a lot at Michigan, also invented by some physics professors at the University of Illinois. I don't know, physics professors like to make things, what can I tell you? So, so that's one way of getting in-class interaction. But this is something that I think we're going to see many, many more versions of in the near future. My colleague here at Michigan, Perry Sampson, is a professor of atmospheric, oceanic, and space science. And Perry has always been an innovator in a bunch of different ways, but often around education. He was one of the founders of the Weather Underground. So if you know about the Weather Underground site online, he was one of the people who created that site and then founded the company. More recently, he turned his attention to his own classes and to the kind of interaction in class that we're talking about here. Perry created first a set of tools that he called lecture tools. And it was really a set of ways for the instructor to interact with the students in their class. Lecture tools included in its early versions things like the ability for students to make notes on the slides in real time on their computer. Those notes were then accessible also to the instructor. Students could ask questions in a sidebar in real time in class. So they're typing questions in a sidebar just like you could right here now in this Google Hangout. And either the instructor or some graduate students who are sitting in the classroom at the same time could be answering those questions, and they can be appearing on a screen. So it allowed a dialogue to be created that was kind of happening through the technology while the instructor is talking or demonstrating something or continuing with the lecture. Lecture tools allowed people to ask and answer questions which were image-based. Perry teaches about weather, and so very often he wants to be able to show people an image, weather map or something like that, and ask them to identify certain features on it, to say, for instance, where do you think in this image the temperature will be highest, or where do you think the winds will be really strong? And it let people mark up images like this and then bring all those answers together so the instructor could see them all and talk about them with the class. So he created this whole set of interactions. He then founded a company called Lecture Tools, and Lecture Tools has since turned into, joined with a larger company called Echo 360. And Echo 360 now offers those lecture tool features as part of a tool that they call the Active Learning Platform now. That system is gradually adding more and more of the kind of functionality that this question asks about. For instance, when students take notes during the class, it actually knows all the notes that students are taking. It knows when they're being taken and so on. And so in a simple way of providing input to the instructor about what people are making notes about, it could do something like take all the notes that every student's written on a slide and turn them into a word cloud. Very simple way of getting some kind of sense of what are all the answers that are out there. That might allow an instructor to see that the main word being used on a certain slide is confused, for example, something like that. This is becoming much more sophisticated now, though. There's a number of groups on this campus who are participating in projects around natural language processing that are thinking about how to put those tools to work so that much richer, more interesting content could be pulled out of student responses to a question. A system I'm quite excited about for large science classes would ask students to write their explanation for a physical phenomenon in the form of a paragraph or so. And then the natural language processing tools would be able to look through all of the solutions or the paragraphs that are put in by students and classify them in a variety of different kinds of ways. You might imagine that one of the simplest ways would be to place them on a scale that is measured from almost certainly not the correct explanation to one that looks really like an expert explanation. Imagine that you got 400 responses from your students in real time. They just sat down and written for 2 minutes a paragraph. And this tool could then place them on some kind of spectrum. Then you, as the live instructor from the class, could pull out some examples. You might want to pull out an example of one that is at the bottom of the spectrum and another at the top of the spectrum and put them up on the screen anonymously. Of course, there's no reason for you to say whose these are. Just to say, here's an explanation, or here are two explanations, and you could ask the students, which one do you think are right? And then you could talk about what's strong and weak about the different explanations. And by having a tool which can somehow sort them very quickly and automatically for you, you'd be able to do this in a real-time way without needing to look at all 400 of the things that come in. So I think there's a lot of interesting stuff that's coming, probably in the very near future, of this kind. I should say those natural language processing tools, they're especially powerful when you're looking at a bunch of samples of writing that are actually all written to the same prompt. It makes the task of analyzing them much simpler because you know they're all about the same thing. So what you can do then is look at their features in order to spread them out in different kinds of ways, in linguistic sophistication, in using certain terms which you know are really important ones for this topic, right? That might be one of the ways that you identify strong examples. So I think we'll be seeing much more of this come out in the future. Another kind of interaction that can happen in class can come from image technology. So in addition to being able to collect student writing through technology, you might also be imaging what's going on in the classroom. And analysis of that imaging could be happening in real time in a way that could allow you to understand what's going on in your classroom in a richer and better way. So imagine, for example, that you're having students do group work in class. Something we often do in a flipped kind of environment is pose a question for students and ask them to work on it for a while. As an instructor, I would usually walk around the room when that's happening and try and keep track of what's going on. But it's often the case that I'll end up getting wrapped up in a question with some individual group and lose track, really, of what's happening in the rest of the room. So you can imagine technology which would recognize when everyone in the room is really working on things and be able to remind the instructor that it looks like everybody else is done. You know, set off some kind of bell or something just to make it clear that it's really time to move along. So it'll be really interesting to think about how we're going to use these kinds of technologies in the classroom in real time in the future. I think the next thing that I'm really looking forward to is this kind of language processing, being able to have students not just give an answer through a clicker, which is a multiple choice thing, or not just as in Perry Sampson's class, be able to mark an image with a point, but to be able to actually respond with an explanation, with text, with ideas, and be able to interact with that in real time in the classroom. I think that would be, that's a really exciting prospect. Probably most important thing about it isn't that we'll be able to do this in class. I think probably the most important thing is that because we can do it in class, we will ask students to write and explain and use language to describe what's going on. So we'll be asking students to engage in a much higher level of thinking when we ask them to write than we do when we ask them to choose A through E in a multiple choice question. It's at least possible for a student to answer A through E with no thought at all, right? It isn't actually possible at all for a student to write 3 or 4 sentences of any kind without thinking. So when we get to the point that most of our interactions are, you go think about this and write something for me, it'll definitely be better for students. They'll definitely do more learning than they do right now. Okay, so that's just a couple examples of things that are happening now in in-class environments, and I can imagine happening more in the future. Okay, a next question. What types of analysis, summarization, modeling, and visualization techniques have I found to be most useful? Okay, it says, of course, this is a practical course. It doesn't intend to dive too deeply into these types of details, but it would be interesting to learn more about what techniques would be most useful for participants to look into as they look at more of the learning analytics data pipeline. So you heard a little bit this week about the ART 2.0 tool. And this is a really great example of this because ART aims to put data visualizations, a lot of them, in front of a very diverse group of people. So one of the central ideas of ART is, one of the central tasks that it has to do is to take data about classes and make it available to students, to faculty members, to administrators, perhaps to the public, to anyone who wants to know about this class. And when you have that diverse an array of audiences, you really want to think about the way you display information. And perhaps make the way you display information flexible so that a person who's going to interact with the system can make choices about how they see the data. So for example, in many ways, I really like tree plots. We've talked a little bit about these tree plots as ways of displaying rich information, rich hierarchical information. But tree plots, you have to kind of learn how to read them, right? And they also ask you to make comparisons of number based on area. And while your eye can do that reasonably well, if you really want to get into details, comparing numbers by showing areas isn't the best way to do it. And this is why some people, for example, don't love pie charts, because they use area to represent something. So it may be that for some users, the tree plot is the right thing to see, and for others, a bar chart comparing all those different numbers that are present in the tree plot would be more appropriate. So when we're building art, we're thinking about a kind of set of personas of different kinds of users. And this is something that user experience design people often do. They sit down when they're thinking about the interface they're going to create, which is what we're talking about here. How are you going to display this information to different people? When they're thinking about that, they're imagining a set of different kinds of users who have different features. So one of them might be a statistician. Okay, so for a statistician, you can pack a lot of information into a data graphic and expect them to be able to extract it. They probably will be very good at doing that. It's something they practice a lot, something that comes natural to them. But another of them might be someone who's, not very numerate, not used to looking at data graphics. And so you really might want to represent the information in a much more textual way, right? It might be much more useful for a user of data like that to receive a list of the top 5 classes that people take before this, for example, rather than getting a data graphic of some kind. Text might be a much more effective way of doing it. So I think you really have to think about audience. And when you think about audience, remember that the audience is diverse and not uniform. And perhaps imagine presenting your data in multiple ways, right? Think about how we do it when we teach, or if you give a talk and you're trying to make a pitch to an audience that you hope will give you some resources or something. You would talk in words. You would provide a summary of what's going on. You would use your voice and gesture to point out and emphasize certain kinds of things. And at the same time, you might be presenting, perhaps on a slide, a data graphic. You don't just put it up and let people figure it out. You talk through it with people. And so thinking a little bit about how the way you present a graphic helps to talk through what it really means is a really interesting kind of idea. We're also trying to present tools that enable people to ask and answer their own questions. So that's another place where flexibility is really important. If we literally made a baseball card for every class and it was exactly the same information, it was fixed and you couldn't explore, that'd be of limited use. Much more useful to allow a person to go in and say, well, I want to know who's in this class. I want to know who takes this class in general. And then I want to say, well, what happens to students who are like me in this class? Or what happens to students who have taken this prerequisite class or that prerequisite class? Do they do better or worse? Which one works better for students, right? So you want the tools to be flexible and be able to explore. It's really exciting to see what's happening with our Art 2.0 application right now. I was just out in the Digital Innovation Greenhouse collaborative space, where 2 of our summer interns, or 2 of our student interns, student fellows that I mentioned earlier, were working with Chris Teplovs, the designer of that, comparing a whole bunch of different ways of looking at things, thinking about how to display a lot of different numbers in an efficient and in easily interpreted way. Really cool to see that kind of work going on. Okay. Another question here. I'd be interested in learning more about the ways faculty members have utilized data in their classroom and whether or how they share this data with their students. Do you as a faculty member in LS&A share your data findings with students in say, a physics intro class? And in sharing this information with the class, do you see their performance change in any way? Another great question. I mean, I think if we are learning things about what happens in classes, of course, one of the reasons we're doing it is to try and improve those classes. So let's say you as an instructor analyze data about your course and you learn something that suggests to you some group of students in your class should change their behavior in order to do better, right? You might, for instance, find out that there's a group of students who regularly start getting ready for the test the day before the test. It's probably true in every class, but you might be able to see that by using data like we have in the modern learning analytics world. If you did that and you found that you could show using data that starting to prepare the day before the test leads to worse performance on the test, then I think you've created an argument that works for yourself for deciding that cramming at the last minute is not a good way to prepare. That's how you know it's true. And there's every reason in the world to share that information with your students. So take it to them and say, you know, I know a lot of you will start preparing for the test a week beforehand, but that others will be busy and have other things on their plate, won't get around to it until the day before the test. So what do you think? Is it better to do one than the other? Get them to think about it, to ask themselves the question, just to get them interested, and then share the data with them to show them what will happen if they do that. I can give you an example from my past. We use online homework systems in physics a lot. They can be great for students because a student can go and work on their homework problems and get immediate feedback about whether their answers are correct or not. Some of these homework systems even have elaborate hint structures that help students figure out how to get them correct. What's great about that immediate feedback is that it allows a student to do their homework until they get it right, right? And so they can work on it as much as it takes in order to get it right and get all their homework right every single week. That's the best thing. That's really what we want, because what we used to do is have students do their homework, they would give it a try and they would turn it in, and a week later we'd give it back to them and say, no, you got 3 of these wrong and 2 of them right. No good feedback, right? So online homework systems are really helpful. They have a drawback though, which is that I think any online homework system that you use, you can probably take the text from the problem that you're asked, put it directly into Google, and find somewhere on the internet that someone has written down the answer. Everybody knows this. All students know this. So they could run off and do their homework very quickly by finding the answers from somewhere else. There are even institutions, quite a few, where students on the campus will get the homework assignment and then create a web page where they write how to do the solutions to this homework, right? You know, they might sell ads on that page and make money. You know, who knows? At any rate, students find that kind of thing an irresistible challenge. So I know that our students recognize that there exist ways of doing your homework that are very fast, but also empty. And I want to talk to them about that, right? So at the start of class, I tell them, there's this wonderful paper that was written by David Pritchard and his group at MIT that studied their homework system, in which they show that people who do their homework in less time than it takes to read the problems end up 2 letter grades below their peers in their introductory physics class. So they use data from their online homework system to identify students who are apparently cheating and showed what the impact on their performance in the class was. Right? They started out at about the same place as everyone else in the beginning of this, and they end up 2 letter grades apart. So when I read this paper a couple of years ago, I started bringing it in and using it as part of my discussion about how you should do your online homework. So just acknowledging openly to students that there are ways you can get answers to these homework questions very quickly, if that's what you choose to do. But if you do, there will be these real consequences. Not consequences imposed because the police will come and get you. Consequences that will be imposed because you actually won't learn what you're here to learn. Right. So I've used that a number of times with my students. They seem to take it reasonably to heart. And at least I think we've been very open and honest about what we know. Another interesting study that was done by some people at the University of Colorado actually talks about the importance of where you sit in the classroom. So what they did was to randomly assign people to seats in a large lecture hall. And actually in the middle of the term, they took the people who were in the front and moved them to the back and so on. And then looked to see whether there was any impact of where students sat in the room on their performance. And what they found is that people who sat in the front of the room actually did significantly better in the class. And it wasn't because they were better students, they were randomly assigned in this case. It's because it's just much easier to be really engaged and pay attention when you're sitting in the front of the room. So this is another example of a kind of analytics exercise that I might share with my students. All of these are aimed at providing evidence to help them become better students, right? The data that we get from learning analytics helps us understand what kind of behaviors lead to better performance of students. And once we know that, I think it's clear we should share it with our students. And how we should share it? Well, depends on who they are, but to some extent, the way we should share it is a way that will be convincing. And for many of our students, using the data is one of the ways of making a really convincing argument. Of course, that argument is most convincing when the data is highly relevant, meaning data from this class on this campus is the most relevant kind of data. So those are some examples of ways in which I've used data in my classes. Now, there are some times when I'm less sure about what to do about data. So let me give two different examples. One occurs when you are recognizing the relationship between student background and unlikely performance. So the kind of performance prediction modeling that we've done a little bit of in this class. The fact that I know that a student who comes in with a relatively low GPA is likely to get a low grade in this class probably isn't an absolute shock to that student, but I really would like to set a different tone and not use this prediction kind of language. Instead, what I want to do is say, what's happened in the past is that people who came in with low GPAs have typically gotten poor grades in this class. So you might take that yourself as a student who's coming in perhaps with a low GPA as a prediction of what's going to happen to you. Or you could learn from experience. You could take what's happened to those students in the past and use it as a lesson to change your own future outcome. You could say, well, whatever I've been doing in the past that's led to these lower grades is not leading to success. The evidence from the past shows that if I don't change that, I'll end up with a low grade here as well. But if you do change it, you could end up with a much better performance, right? So that kind of learning from experience, even in a place where it might look like the prediction's going to be bad, might be a way of helping a student move toward a better than expected kind of outcome. But it's a little tricky to know what you should say to a student for whom the prediction or the experience from the past is kind of negative. It's kind of not very good. So another great example of that, of course, are the gendered performance differences that we see in our introductory science classes here at Michigan. I began work on that because I really am dedicated to increasing the representation of women in science. Spent a lot of time and energy on it. And so I wanted to see what it was like. When we saw what it's like and how widespread it is, it created a kind of dilemma for us. It made me ask, is talking about this problematic? Is it going to lead to this outcome? Is it going to exacerbate it? Is it going to drive women away from science? So part of what convinced me that I should talk about it is that there is research that shows that when people are in circumstances that lead to negative outcomes like this, telling them about it usually leads to better outcomes. So if, for example, people are in a situation where they're facing overt discrimination, making sure they recognize that they're actually facing overt discrimination helps them to overcome the impacts that might have. So when I learned about some research that was like this, it helped to convince me that it was better to talk about this rather than to not talk about it. And I think my general sense is that that's the case almost all the time. Now, it's also true that the gender performance differences that we have discovered place an obligation on us to be working to do something about them. We think that the structure, I think, that the structure of our classes is part of what causes these gendered performance differences. And so one of the projects that I'm working on here on campus is trying to change those structures to see if we can make those go away. But in the meantime, I do talk to students about these things. I think it's important that they should know about it. And many students find it in a certain way validating that something that they felt was happening really is happening. And that it's not just happening to them as an individual, but it's kind of happening in a broader sense. What's going on isn't really about them. It's really about the structures that are being placed around this whole group of students. So lots of things to think about. Have we been able to change people's behavior and performance is another part of this question. In sharing this information with a class, do you see their performance change in any way? And there the answer is really Yes. A good way of showing this has been through the eCoach system. So in eCoach, much of the advice we're giving is tempered by data in exactly this way. So we're talking to students, we're saying, if you want to be more successful than you would be without us, you're going to have to change your behavior. And how should you change your behavior? Well, let's show you some data about what it takes to be successful in this class. And the data might be data that says, if you regularly work on your homework instead of doing it all in one lump, you'll actually do better. So changing a student's behavior to these better kinds of behaviors is all you really have to do in order to improve performance. So what we've done in eCoach is to show that students who interact with the system a lot, who actually read the advice, do change their behaviors. And not only do they change their behaviors, but those changes in behavior lead to better outcomes. So in our very large 2,000 student statistics class here on campus, students who interacted heavily with eCoach improve their performance over students who never use it by about a half a letter grade. It's really substantial improvement in performance. And we can see that it's not a selection effect through a variety of different methods. And we can also show that the thing that leads to this improved performance is actually changed behavior. They behave differently because of the kinds of advice that we're giving. So I think you can make these kinds of arguments with students. You can change their behavior, and changing their behavior, of course, can change their outcomes. So I think it's a very powerful kind of approach to take. Okay, with the data in this state, someone asks, I'm less confident in the results of analysis of majors in the course pathways analysis. The list of the top 10 majors for Physics 140 is EECS, with about 10% of the population having that major. However, the code is skipping all the NA people, which is 25% of the students who took that class. Okay, that's a great kind of question. So if you want to do an analysis of data for something like Physics 140 and ask, what do people go on to major in? The first step is to make sure you understand the data set and what it's telling you. So there are a very large number of NA people in the data set, and that's because a very large number of the people in the data set have not received a degree yet, right? So you want to make sure that if you want to know what fraction of people receiving degrees are have a certain degree, you want to make sure that you're only including people who've actually received a degree, so that you get the fraction of the people who received the degrees. So that's what's going on here. The NA records in this data set often reflect the fact that they just haven't completed a degree yet. Okay. There's another question here about these NA records. That's a little bit, I guess it's another variant on that. Any data set that you take, any snapshot, any moment when you gather data about students, you will have a mix of different kinds of things in it. You'll have students who haven't completed degrees yet, and so on. So we've given you this big data set, which is built on real students over some specific time period. So it will include some people for whom you're seeing only the last semester. It will include other people who've just arrived and haven't gone on to graduate yet, right? So if you wanted to ask a question like, a more precise question like, among all the people who take Physics 140 and have completed a degree, what did they go on to major in? You would have to extract a subset of students for whom you have actually all that information. You know that they took Physics 140, and you know that they went on to complete a degree. Then you'd be able to answer this kind of question. So very typical kind of problem. You need to specify exactly what you're asking. If we're, so in a certain sense, the answer that's described here, only 10% of the people were EECS majors and 25% didn't have degrees. It's an accurate answer to a different question. So the different question is, among the people who've taken Physics 140, what degrees have they received? All the people who've taken Physics 140, not the ones who've completed degrees, right? So among all the people who've taken Physics 140 in this time period, 25% of them have not received degrees. So that's true. It's just not the question that I think maybe the person who was asking this answered or was really asking about. Okay, so it's a kind of refinement question that you have to make. It would be fun, actually, probably to generate some examples of this. How would you refine the data set to be able to answer specific kinds of questions? And of course, any kind of question that you answer like that is fixed in a certain space and time. So for example, if we ask this question about what do people go on to major in when they take introductory physics. The answer we would get if we looked in the years from 2000 to 2006 would be different from the answers we would get if we looked from 2010 to 2015, because we actually have a whole set of new majors that we didn't have before. We have degrees in data science, we have degrees in informatics, things that didn't exist before. Not so many of them have gone away. Universities like this tend to agglomerate new things rather than have things go away. But things do change with time, no question about that. Okay, one last question that I have here. Do we use Hadoop with R for analyzing big data? Big data like online student transactions in e-learning platforms. So I personally don't right now. And that's partly because the data sets that I work with, while they're large, are not really big data sets. I think we discussed this a little bit in the class. They're large data sets, but not gigantic data sets. Some of my students have used those kinds of structures to handle larger data sets, and in particular to handle more complex problems. So I've had groups of students work on a couple of analyses that got computationally challenging. All of them involved kind of interactions among students, where not only are you looking at the individual records of students, but how they kind of connect to one another. One of them was a senior thesis project that my student Kar Epker last year wrote. Kar was a computer science major, and he wanted to do a project on education data and that would use some of his computer science skills. So he did a very interesting analysis of the network structure of the student experience on campus. So there are many ways you might do that, many kinds of networks that you might try to draw. We did something very simple and something very clean. Because we have records of all the students on our campus and the courses that they take, we know with great confidence when two students took a course together, right? So we can use that connection, these two students took a course together, as part of building a network among students. And we can ask, among all the students who are on campus, which ones have you ever taken a class with? And how have you connected to students who major in your own major or major in other disciplines? Are you more likely to take classes with people in your major or with other majors? Which majors are most connected? So it turns out that things like physics and math are pretty closely connected. Lots of people who are math majors take courses with physics majors with math majors. But other disciplines are much more remote and isolated. So Kar built this network, and it was actually a large network, a lot of different connections among a lot of different people. So he had to use these kinds of more advanced big data methods in order to be able to do his calculations. He actually did it on a modest supercomputer here at Michigan. That made it a great challenge for him. I mean, a great project for him. He's a computer scientist. He wanted to learn how to use these kinds of methods. What we learned in that project was really interesting, even though we kind of only did the first rounds of it. We were thinking in doing that project about a specific question. We wanted to be able to represent for every student some kind of measure of the intellectual diversity of their experience on campus. What we were thinking is, most of the time when we represent the quality of a student, we just measure GPA. We make a performance measure of their quality, right? Of the nature of the student, right? Stretch it out on an axis from 0 to 4. But there are many other aspects of a student experience, and we might like to be able to represent those. And one other aspect of a student experience is intellectual diversity, right? Intellectual diversity, at least in principle, could be quite orthogonal to performance. You might have some people who do very well on performance, but only study one thing. And you might have someone else who is really diverse in their study, but maybe doesn't perform so well. Or of course, you could have people who do both, right? So we think of these as potentially orthogonal kind of measures. So Kar set out to make a measure of the intellectual diversity of the interactions of a student by using this network of course co-enrollment. He found a lot of interesting things. First of all, if you look at majors, you can see that some majors are quite isolated and other majors are very connected across campus, right? Just in general, on average, for all the students in that major. Here at the University of Michigan, the most isolated major among all the majors on campus is musical theater. So students who are musical theater majors spend almost all their time taking classes just with other musical theater majors. Even within a discipline like that, though, there are some students who are much more connected and some students who are much less connected. And the single student who is the most connected musical theater student in the data set that we looked at was a student who was a joint musical theater and English major. So this measure of intellectual diversity is reflected in their transcript in a sort of obvious way, but it's great to see that a measure like that is also actually picking up something real. Right? It's not just noise in the measure at all. It's a real kind of thing. Then there are some majors that are very, very broad and very interconnected. In fact, we have a general studies major, which has almost no real requirements in it. And what that means is that students in general studies are actually as likely to take courses with people in any other major as they are to take courses with general studies students. So they're kind of spread out pretty broadly through the campus. So these kinds of measures, which require using a little bit of big data kind of technology, I think are part of the future of how we'll characterize students. I've been hoping that we would find 4 or 5 different measures that really reflect things orthogonal to raw performance. My hope is that if we can do that and we can convince people that these measures are all relevant and important, that a student, instead of working really hard to climb up that GPA axis, might recognize that there are actually other things like intellectual diversity that are important, and furthermore, that would be reported by the university. If a student had 5 or 6 different measures of the quality of their experience, then they might actually look to do optimally well in all of them, trading off perhaps GPA a little bit against intellectual diversity, knowing that, okay, maybe you have a little bit lower GPA, but you have really great intellectual diversity, right? So it might help students to have a more balanced kind of approach to what they do, instead of thinking that everything in their life hangs on the grades they receive and nothing else. Right? So that's one example of a big data kind of problem. Another example of a big data problem is a project that we worked on to actually to try and get away from GPA as a measure of student performance. Perhaps I'll even record a segment about this because it's an interesting challenge. What do you do if you want to try and replace GPA? The fundamental problem I see with GPA is that it averages together the grades that students get in all their classes as if they meant the same thing. We know from looking at this data, among others, that average grades in classes vary a lot. So when we average them together, we're doing something kind of dumb. We know they're not the same, but we average them together as if they were the same. So this drives students toward classes where the average grade is high, because they know they're going to get a higher average grade and that we're going to count that as if it was the same as every other class. So I would like to remove that dependence at all on average grade on our measure of student performance, so that the average grades could be whatever, and it wouldn't help or hurt any student to take a course that gave low average grades or high average grades. So we did a project to attempt to do this by basically building a model that describes every grade a student receives as a combination of a student effect, how successful the student is on campus, and a course effect, which is a measure of how much the course affects the student's grades. Doing that requires building a really large matrix, which has all the grades given to all the students in all the classes, and then needing to be able to invert that matrix. So that also required kind of some sort of supercomputer applications. Now, there's no question that as we get into things like online student interactions, where every student is maybe interacting millions of times in terms of click streams and so on with a class during the course of a term, and then there are many students in the class, then the problems will become much more problems with big data. And you may see people needing to move into those kinds of spaces. I've done that less in part just because I'm a very practically minded person. And I know an awful lot of questions that I haven't answered yet in these sort of not so big data sets. So that's where I'm spending my energy now. And if I find a problem that needs to go into that big data area, that's when I'll do it. But until I run out of questions in this space, I'll keep working on projects that are of about this size. Okay, we've come to about the end of our 1 hour office hour segment. Lots of great questions this week. I'm happy to have had the chance to answer them. Next week in Practical Learning Analytics, we'll be telling you a little bit about our attempts to do data sharing across the CIC. That should be interesting for you to see. That'll be the 4th and final week of this kind of mid-period where we're asking you to go out and work on the data. We're really looking forward to seeing what you produce. So we'll be sending out some suggestions for how you might share that information with us. And then we'll be entering the last 2 weeks of the class when we'll provide some kind of wrap-up both of what happened here in the class and of what we think is happening and where learning analytics is going. So I look forward to that.